You know that feeling when your phone or your laptop starts getting really, really hot? Okay, so let's dig into that. Because when you scale that little problem up to a global network of data centers, the ones running our entire digital world and all this new AI, that heat becomes an actual crisis. It's the sign of a massive energy problem, and it's pushing our technology right to the edge.
For decades, the whole story of computing was just about getting faster. But that's not the game anymore. Now, the real bottleneck is power. The traditional silicon chips, the very foundation of, well, everything, are hitting a hard wall. The problem isn't just about making electrons move faster, it's that just moving them at all creates a totally unsustainable amount of waste heat.
And just how bad is it? Well, take a look at this number. To do a single AI task, something like identifying one object in a complicated picture, a high-end GPU can burn through over 153,000 joules of energy. That's the brute force way of doing things, and it is incredibly inefficient.
But what if you could just not use electrons? I mean, for decades, that's all we've done, push them through tiny little wires. But now there's a new challenger in the ring, and it uses particles of light, photons, to do the work instead.
And the difference is just staggering. An experimental photonic chip did that exact same AI task using a little over 2 nanojoules. Now that's not just a little bit better, it's over 70 billion times more energy efficient. To put that in perspective, that's like comparing the energy from a massive lightning bolt to the tiny flash from a single firefly. This gap is really the core conflict that's going to define the next decade of computing.
So what is really holding silicon back? It turns out it's not just one thing. We're looking at two massive, kind of existential threats to its dominance. You can think of them as two giant walls that it has to somehow climb over to keep getting better.
First up, you've got the economic wall. I mean, the cost to design just one cutting-edge chip has just exploded to over $500 million. Then you have the physical wall. When you get down to the 3-nanometer scale, you're practically working with individual atoms. Waste heat becomes a critical point of failure. And even worse, the electrons start to, well, misbehave. They start quantum tunneling, which is a fancy way of saying they basically teleport through walls they're not supposed to, causing all sorts of data corruption and errors.
So with silicon running into these major limits, how do the new guys stack up? We're going to put them head-to-head in a little data showdown. Let's do a direct comparison of all three, silicon, photonic, and quantum, on the two metrics that really matter most, raw speed and energy use.
The difference in scale here is just mind-boggling. A normal silicon transistor takes somewhere between 10 to 55 nanoseconds just to flip on or off. In contrast, an entire photonic system can finish a whole AI task in just 31 times picoseconds. And a picosecond is 1,000 times faster than a nanosecond. We are talking about a fundamental leap in sheer speed.
Let's try to visualize that gap for a second. In the time it takes for one single silicon transistor to do its job, just 1 nanosecond, a photonic chip could have already knocked out around 32 different operations. It's just a faster way to move information, plain and simple.
But what about quantum? This quote right here nails the difference perfectly. Photonic speed is all about pure velocity, just doing things incredibly fast. Quantum speed is a whole different beast. It's an algorithmic advantage. Think of it this way. To solve a maze, a classic computer tries every single path, one by one. A quantum computer somehow can explore all the paths at the same time. This lets it solve these very specific, crazy problems that would take a normal supercomputer millions of years. And hey, if you thought the speed gap was big, the energy gap is a canyon. This chart just makes it brutally obvious. That huge bar on the left, that's the energy a GPU chugs down. In that tiny, tiny sliver on the right, you can barely even see it. That's the photonic chip. This isn't just a small improvement, it is a revolutionary jump in efficiency. But quantum computing has a catch, a really big one. To keep its delicate qubits stable, these machines have to be cooled to just 20 millikelvin. That's a temperature colder than the vacuum of deep space. And the refrigerators you need to do that, they are enormous, and they consume an insane amount of power, sometimes over 32 megajoules. So any energy savings you might get per calculation are just gone. Okay, so we've seen the data. Photonic is wicked fast and efficient. Quantum is super powerful but really specialized. And silicon is everywhere, but it's struggling. So what does all this mean for the future?
Let's try and forecast what the computer chip of 2030 is actually going to look like, and we'll use market readiness as our guide. This table here, this is the technology readiness level, or TRL, and it tells a really important story. See, silicon is at a 9. It's mature, it's everywhere. Photonics is sitting at a 6 or 7, which means it's just starting to get into early commercial use, mostly for things like high-speed connections in data centers. Quantum, though, it's way down at a 3 to 5. It's still an experimental tool for researchers, not something you're going to have on your desk anytime soon. Which brings us to the big question of this whole explainer, right? With all these different strengths and weaknesses and levels of maturity, which technology is actually going to win the future of computing? And the answer, when you look at all the data, isn't about one winner taking all. Instead, the most likely future is a really sophisticated mashup of all three technologies working together in what you might call a new hybrid architecture. What that really means is it's not a replacement, it's a team-up. This whole chip war is probably going to end in a truce, where each technology just specializes in what it's absolutely best at. So let's think of it like a team. Silicon is still going to be the brain, right? Handling all the general logic and memory. Photonics, that becomes the nerves, the super fast, super efficient communication system that connects everything. And quantum, that acts as a specialized oracle, a resource you access through the cloud when you need to solve those ridiculously complex problems, like discovering new drugs or designing new materials. So this is a pretty fundamental shift in how we even think about computing. We're moving out of this era where one big piece of silicon tried to do everything, and we're moving into a new cooperative way of doing things. So the main takeaway here is this. The future isn't about replacing silicon, it's about evolving it. Silicon's time of doing everything all by itself is ending, but its job as the brain isn't going anywhere. Photons take over as the nerves to solve that speed and energy crisis, while qubits become this powerful oracle for problems we couldn't even have dreamed of solving before. And that really brings us to the new frontier. The basic physics, that's pretty clear. The biggest challenge ahead of us now is an engineering one. The question that's going to define the next decade is no longer which technology is the best, it's how on earth do we wire these three incredible but totally different technologies together into one system that actually works.